Hello everyone, welcome to BADM A724 Quantitative Methods and Business Analytics. This is lecture 12 and this is your instructor for the class, Dr. Frank Tian Shi. In this lecture, we're going to cover time series and models and decomposition and some data reduction techniques. Okay, including time series models, moving average, exponential smoothing, data reduction, clustering, PCA, factor analysis, and cluster analysis. Okay. First, time series models. Actually, we talked about this before a little bit, in previous lectures. A time series is a series of data points indexed in time order, a sequence taken at successive equally spaced points in time. For example, the heights of ocean tides, counts of sunspots, daily closing value of Dow Jones Industrial Average. They're all time series data. Okay. Time series are very frequently plotted via a line chart. Line charts, as we have seen before, is best in presenting time series data. Okay. Time series forecasting is the use of a model that predict the future values based on previously observed values. Time series data have a natural temporal ordering that's already built in. So, time series models are generally reflect the fact that observations close together in time will be more closely related than observations further apart. So later development has a better indication of the future trend. Time series decomposition, an important technique for all types of time series analysis, especially for seasonal adjustment, is time series decomposition. Time series decomposition seeks to construct from an observed time series a number of component series that could be used to reconstruct the original by additions or multiplications, where each of these has a certain characteristic or type of behavior. Okay. For example, time series are usually decomposed into the trend component, right? The cyclical component, the seasonal component, the irregular component or noise. The trend component is very useful in business, as we can see from the trend whether the product sales, for example, the sales of a certain product line, or the business of this company, is in an uprising, is upward trend or is downward trend. Is this product going into a rapid expansion growth period, or it has reached maturity or even decline? Okay. Time series data can be decomposed into cyclical component. The cyclical component gives us the cycles that the data may follow. So we can look at the past cycles and predict the future cycles. In economy, there's always ups and downs, expansion and recession, and so are the time series data for many product lines, companies, industries. Then there's the seasonal component we can decompose time series data into. The seasonal component could refer to the seasons, the 4 seasons of the year, right? Or holiday seasons, shopping seasons, other seasonal components. And then there's a irregular component or noise that we cannot really explain at this moment, but we regard them as noise. Application of time series decomposition. Time series decomposition can be applied in policy analysis, by our government at different levels. They can forecast, for example, the future production of biofuels. Okay? and the optimum length of the moving average, and the seasonal length, and the start point. We can use that for time series decomposition. Next, let's talk about the moving average. Moving average, MA. It is a widely used indicator in technical analysis that helps smooth out price actions by filtering out the noise from random price fluctuations, because there are always going to be price fluctuations or noises from the data. If we use a moving average, we can weed out those noises. A moving average, MA, is a trend following or lagging indicator because it is based on past prices. It's trend following. It follows the trend and it lags behind the trend. Okay? There are two basic and commonly used moving averages. One is called the simple moving average, or SMA, which is the simple average of security over a defined number of time periods. Okay? Just simple average. And the other is called exponential moving average, or EMA, which gives a bigger weight to more recent prices, or whatever you're measuring. Okay? This example of a moving average, simple moving average. You can see here these are the closing price of a certain stock from day 1, day 2, all the way to day 9. Right? And this column is for 10-day simple moving average, and this is the value used for simple moving average. If we want to take a moving average over 10 days period, right? So we can go from skip 1 to 9. Then on day 10, we take day 10's price, closing price, right? And the 10-day simple moving average, we average all the 10-day data, we're going to get 25, right? And that is the average of day 1 through day 10. That's all these values here, okay? And then on day 11, we have the closing price on day 11. Then we're going to average the day 2 through day 11. Remember, this is a 10-day moving average. So we'll start from day 2 all the way to day 11. That's also data from 10 days. So the average is 25.8. The next day, following day on day 12, the stock closing price is 30. And we're going to average day 3 through 12. That's from here, 24, all the way to 12. That's also 10-day period. And then the price of that, average of those 10 days is 26.6, and go on. Right? You can see there are fluctuations, in the first 10 days, or in all 15 days, from as low as 20, right, to as high as 30. Right? If you do an average 10-day average, simple moving average, you see the price is not fluctuating that much. We filtered out the noises and getting a better trend indication of the trend. So this is example of a 10-day moving average, simple moving average. Okay. Exponential smoothing. Exponential smoothing is a rule of thumb techniques for smoothing time series data, and it applies as many as 3 low-pass filters with exponential window functions. Okay? It's a very popular scheme to produce a smooth time series. Right? Single moving averages, the past observations are weighted equally, the one we just talked about. Exponential smoothing assigns exponentially decreasing weights as the observation get older. So newer observations get more weight, and older observations get less weight. In other words, recent observations are given relatively more weight in forecasting than the older observations. That's exponential smoothing. Okay. Next, let's talk about the data reduction and clustering. Yeah. In machine learning and statistics, Dimensionality reduction or dimension reduction is a process of reducing the number of random variables under consideration via obtaining a set of principal variables. It can be divided into feature selection and feature extraction. Feature selection and feature extraction. Why do we need data reduction? Because sometimes we do just have too much information, too many parameters, too many aspects, too many things to grasp, right? We want to use this data reduction and clustering techniques to reduce the dimensions, you know, and we group some of the parameters, variables together, right? And we group some of the observations together. So that's why we use data reduction and clustering techniques. There are two types of them: feature selection and feature extraction. Okay? Feature selection. Feature selection approaches try to find the subset of the original variables, also called features or attributes. Right? There are three strategies: filter, that is using an information gain filter, and a wrapper, that is search guided by accuracy approach. The embedded uh, approach, that is, the features are selected to add or be removed while building the model based on the prediction errors. The feature selection. Feature extraction, though, transforms the data in the high dimensional space to a space of fewer dimensions. The data transformation may be linear, as in the principal component analysis we can just cover next. Okay. Principal component analysis, PCA, yeah, is a statistical procedure that uses an orthogonal transformation to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components, or sometimes principal modes of variation. Basically, we want to convert the set of observations to a fewer, and there are possibly correlated variables into a set of values of linearly uncorrelated variables. These are the principal components. The number of principal components is less than or equal to the smaller of number of original variables or the number of observations. So we are reducing the data, simplifying the data. Okay? This transformation is defined in such a way that the first principal component has the largest possible variance. That is, accounts for as much of the variability in the data as possible. And each succeeding component in turn has the highest variance possible under the constraint that it is orthogonal to the preceding components. The resulting vectors are an uncorrelated orthogonal basis set. PCA is sensitive to the relative scaling of the original variable. PCA is mostly used as a tool in exploratory data analysis, EDA, and for making predictive models. PCA can be done by eigenvalue decomposition of a data covariance or correlation matrix, or a singular value decomposition of a data matrix, usually after mean centering and normalizing or using z-scores, the data matrix for each attribute. Okay. Next one tool that's used is called factor analysis. Factor analysis is a statistical method used to describe variability among observed correlated variables in terms of a potentially lower number of unobserved variables called factors. For example, it is possible that variations in 6 observed variables mainly reflect the variation in 2 unobserved or underlying variables. Then we can use factor analysis to change those 6 variables into 2, that could be unobserved or underlying. Okay. Factor analysis searches for such joint variations in response to unobserved latent variables. And the observed variables are modeled as the linear combinations of the potential factors plus the error terms. Right? So we want to find factors or latent variables, unobserved latent variables. Factor analysis is not used to any significant degree in physics, biology, and chemistry, but is used very heavily in psychometrics, personality theories, psychology, marketing, product management, operations research, and finance. Okay. Factor analysis is related to principal component analysis, but the two are not identical. Okay. PCA is a more basic version of exploratory factor analysis that was developed in the early days prior to the advent of high-speed computers. Cluster analysis. Cluster analysis or clustering is the task of grouping a set of objects in such a way that objects in the same group, called a cluster, are more similar in some sense or another to each other than to those in other groups or other clusters. Okay. Its main task of it is a main task of exploratory data mining and the common technique for statistical data analysis used in many fields, including machine learning, pattern recognition, image analysis, information retrieval, bioinformatics, data compression, and computer graphics. It's quite very useful, very hot. Okay. Cluster analysis itself is not one specific algorithm, but the general task to be solved. It can be achieved by various algorithms that differ significantly in their notion of what constitutes a cluster and how to efficiently find them. Okay. Besides the term clustering or cluster analysis, there are a number of terms with similar meaning, including automatic classification, numerical taxonomy, Botryology, and typological analysis. So just so you know. Okay? In data mining, the resulting groups are the matter of interest. In automatic classification, the resulting discriminative power is of interest. Okay. Cluster analysis was originated in anthropology by Driver and Kroeber in 1932 and introduced to psychology by Zubin in 1938 and Robert Tryon in 1939, and famously used by Cato beginning in 1943 for trait theory classification in personality psychology. You guys might have tried that sometime in the past.